We want to talk about finding the derivative of an inverse trig function. So perhaps we should just refresh our memory what these inverse trig functions look like, shall we? So our trig functions, of course, are like cosine of x, sine of x, tan of x, and the reciprocal ones. So remember, in a normal function like this, the input is my angle. It can either be in degrees or in radians, and the output is a ratio of sides. In this particular instance, cosine is the ratio of sides of the x value, or the adjacent side to the angle, divided by the hypotenuse, or the rotating arm. So for example, I could have the cosine of pi over 4 radians is equal to square root of 2 over 2, right? That's my angle. That's my ratio of sides. Quick picture, here's my angle. Pi over 4, of course, is 45 degrees in degree land. Here's my ratio of sides, square root of 2 over 2. So in inverse, if I'm switching the x and the y, and then I solve for y, to get y by itself, I need to undo the cosine. Well, to undo any function, I do its inverse. The inverse of cosine, we sometimes call it arc cosine. Sometimes we use this horrible notation. Cosine with a little -1. I say that's horrible because that looks like an exponent and it's not, which is why most math people prefer this notation, arc cosine. But those notations are comparable. They both mean inverse. Okay? Now, the thing to keep in mind here, I switch the x and y. This x now is my ratio of sides. This y now is my angle. So a cosine turns an angle into a ratio of sides. Its inverse turns a ratio of sides into an angle. So now let's do the fun stuff. Let's take a derivative of an inverse trig function. There are formulas. If you look at a formula sheet, you will find formulas that allow you to find the derivative of an inverse cosine, or an inverse sine, or an inverse tangent. But let's figure it out for ourselves, shall we? Let's do it. Let's say that f of x is cosine of x. Okay, so the f of x is my y, so I'm going to call that my x. X I'm going to call my y. Now I could keep going and solve for y as I did here, and say y equals the arc cosine of x, but I don't know how to take the derivative of that. And I do know how to take the derivative of this. So I'm just going to dive in and take the derivative of both sides. Now, since y is not isolated, I have to remember the chain rule, right? A little implicit differentiation action is going to happen. So let's take the derivative of both sides. Derivative of x is 1. Derivative of cosine of something is the negative sine of something. And then the chain rule times dy dx. All right, I'm going to get dy dx by itself. Just going to divide by negative sine of y. All right, well, I should be happy, but my function, my derivative is now in terms of y instead of in terms of x. So, whoops, I dropped a negative, didn't I? I'm just going to put that out front. Is that legal? So let's see if I can rewrite this expression in terms of x. How am I going to do that? Well, I'm just looking up the page and I'm seeing, oh, well, x is cosine of y. Is there a relationship between sine and y and cosine of y that you can think of? Think back to our trig identities. More specifically, think back to Pythagoras and the Pythagorean or Pythagorean trig identities. And pause the video and see if you can play around with this.
Moves like a fist through traffic, anger and
Da, 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 da. Cosine squared theta plus sine squared theta equals 1. That is such a handy and cool Pythagorean trig identity. And it works because if you have an angle, that's a little theta there. Let's say it's a unit circle. I think you would agree, Pythagorean theorem, x squared plus y squared equals 1 squared, or x squared plus y squared equals 1. But look, the cosine of theta is x. The sine of theta is y. So that's where that identity comes from. All right, let's see if this is going to help me in this case. I think it's going to. I have a sine of y. I want it to be in terms of x. I know x is equal to the cosine of y. So let's just throw in a y here because this has to be true. And let's solve for sine of y, shall we? I'm going to subtract my cosine, take the square root. So I have the sine of y equals, technically it's going to be plus or minus that, but we're just going to go for the principal value. Okay, we're getting close. Oh my goodness. Do you see what I see? Pause the video and look. Remember, this is cosine of y squared. What can I replace cosine of y with? Yeah, cosine of y is x. So the sine of y is equal to the square root of 1 minus x squared. Holy cow. Oh my goodness. Well, if that's the case, then I can replace this sine of y with that expression. And I have dy dx equals, don't forget that negative, 1 over the square root of 1 minus x squared. We just derived a cool rule that allows you to take the derivative of inverse cosine. Now, you don't have to do this every time because we have these cool rules. Let's write them down. Here they are. And they are on the derivative shortcut sheet that I already gave you. So the derivative of arc cosine or inverse cosine of x is -1 over the square root of 1 minus x squared. We just derived that. The derivative of arc sine of x is the same except it's positive. The derivative of arc tan of x is 1 over 1 plus x squared. I think you could figure out how to derive arc sine of x. We do it exactly the way we did it for arc cosine and arc tan also. The other way to come up with these is to use the cool inverse function derivative theorem that we created and discovered. So you can play around with that as well. But let's do some examples and see how these work. Okay, if f of x equals arc sine of 3x, find f prime of x. Again, remember that notation, you also could see it like this. But no one I know likes that notation, but you will see it occasionally. All right, I'm just going to use my cool little rule here that I just discovered. Derivative of arc sine is 1 over the square root of 1 minus x squared. I'm hoping that you're realizing that I've got an inside, so a chain rule is going to kick in, right? So pause the video and see if you can use this rule to find the derivative of this function. All right, here we go. So the derivative is going to be 1 over the square root of 1 minus. So my input here is not x, but it's 3x. Quantity squared. And then there is going to be a chain rule because I have an inside. So that was the derivative of the outside times the derivative of the inside. And then I think we can just simplify this nicely. to give us 1 minus 9x squared. And there's my derivative. And just a reminder, friendly reminder, this is the square root of this whole difference, right? Remember, order of operations, you would have to subtract those before you take the square root. You cannot take the square root of each one of those. So that's as far as you can go. We've gone about as far as we can go. All right, let's try another one. Okay, now I'm just getting crazy. Try to find this derivative. I'm just going to use Leibniz's notation because I'm in the mood. So the derivative of an exponential is the natural log of the base times the exponential as it is, and then times the derivative, chain rule, of that inside. The derivative of arctan is 1 over 1 plus, my input is just x in this case. So I'm all set. If you want, you can put that whole kit and caboodle in the numerator just to make it look pretty. And there you go. So now that you know about these rules, just be on the lookout for them. They can be kind of fun. They look more intimidating than they are.
A little bump to the momentum. It's just a little lump, but you feel it in the creases and the shadows.